Hello, everyone. Thank you for joining and welcome. My name is Dušan. I'm an engineer at ELSYS Eastern Europe with a little over 6 years of experience in digital design verification. And in this session, I'll be talking about the vertical reuse of formal verification components. So our agenda will consist of a brief introduction, after which I will talk about some of the basic building blocks of SoC verification model. Then I will present some techniques you can use while designing your formal verification components to make them as reusable and flexible as possible. And after that, I will provide some practical examples of these techniques being applied and basically the benefits they bring. So, as I mentioned, I'm a member of the ELSYS Eastern Europe. We are a service company located in Serbia, in Belgrade and Novi Sad. We are an approved ARM design partner. We specialize in design and verification of electronic systems. We were founded in 2004 and now have over 200 engineers. So on this slide here, basically you can see a summary of our 17 years of expertise, which includes which ranges from digital to analog, from hardware to firmware, includes various methodologies, tools, and languages. So these slides will be publicly available. In case you have any questions about the company, just feel free to contact us at our booth. And now on to the topic. So everything I will talk about today relates to the SoC designs which have some kind of an IP, which is a very good target for formal verification. And if that is the case, then the usual verification strategy would be to use formal verification to verify that block, that IP, and then focus on simulating use cases in some practical scenarios on top level. In case there is some subsystem can be identified, then the usual approach is to use co-verification of formal and simulation, depending on how complex the subsystem is. You can do probably bug hunting to a certain extent. So when we say vertical reuse of formal verification components, we actually mean taking the environment, the checkers, the constraints, basically anything we can from the formal level, formal block level verification, and reusing it in these higher levels. To understand how and why we should do that, let's briefly go over the goals of each verification level. So basically on the block level verification, if you're doing formal, the goal would be first to define some set of valid operating conditions. So we have to define how our block is intended to be used, and then basically exhaustively verify that block, the block's features. And on the top level or higher levels, the goal is mainly with respect to these sub-blocks. The goal is mainly to verify the integration of those blocks and the connectivity into the system, and to check that their operating conditions are not violated. So basically to ensure that the block is used correctly. So how can we benefit from vertical reuse? Well, one thing, all of those operating conditions on block level are usually specified via assumptions, which we provide to our formal analysis tool. So they are already there. So it would make sense to actually take those assumptions and reuse them on some higher level, but not as assumptions, but as checkers. So everything we assume that will be true on block level we can actually check that it is true when we run some higher level tests or use cases. So that's one way we can benefit from the reuse. The second one is if we're doing a thorough, exhaustive block level verification, then we surely have defined a good set of cover points which need to be checked on block level. So if we want on the top level to make sure that our tests exercise that block sufficiently, we can make use of the coverage which is already there and which targets some of the most basic features. So what we want to basically show here is how to make this migration, the migration of everything we did on block level, as easy as possible to do on higher levels. And to show this, we'll make use of a simple design example. In this case, it is a command interpreting module. So this particular module receives a command on its input. It interprets this command, and based on it, it can access some register bank to modify some registers, or it can issue a serializing command to this serializer. What this does is it basically converts some bit vector into a serialized stream of bits. And as you can see, this serializer is configurable, and some of the configuration comes from the register banks. Now, in this example, basically all three IPs here shown here are very good targets for formal verification, but we decided to go with the serializer. So short recap on the formal verification components. Basically, formal verification components are nothing but the checker modules with identical interface to the one which the design has, with the exception of all ports being inputs. So what we want to achieve is to kind of stick this checker to the module so that it monitors all activity in the actual RTL, but in no way interferes with the logic itself. Since we are doing this for the formal analysis, the way of how we connect those two will have to be a little bit different from, let's say, the way we get used to using UVM. And there are several ways we can do this, but in this example, we decided to go with the system verilog bind command. One example is shown here. So for example, this command will bind an instance of serializer checker into our serializer design. So every time the serializer is instantiated, it will come with its own internal checker, binded to it and connected, ready to monitor and check its activity. After we do the elaboration, we can see on the picture to the right what the structure is going to look like. And for our block level verification, formal verification, we don't really need any wrappers or test benches. As you can see here, the top elaboration entity is actually the design itself. It's the serializer. And as you can see, it has inside it bounded serializer checker monitoring its inputs and outputs. And optionally, you can also monitor the internal signals if you're doing white box checking. Now, what do we have to do in addition to compiling this design? What do we have to do to make this happen, to make this serializer checker appear here? Basically, all of these files which are used to compile the design are already there. You need to have them if you want to do anything with your design. But in addition to include your checker, you would have to provide this additional file list, which basically compiles the checker itself, and it binds the checker to your module. So the next step would be to create the properties and assertions for the actual requirements. We will not go into the details there. Just to give a couple of examples. So this block has two outputs, one which is the data valid indicator, which is supposed to be active whenever there is a serialization ongoing. And let's say that this checker here, correct serial data valid, is in charge of checking that requirement. And it also has this serial data output, which basically outputs a stream of serialized bits. And again, without going into the details of the actual checker implementation, let's just say that this here property is in charge of checking the correct behavior of that output. Right. So that would take care of the first part in our requirements, saying that we need to exhaustively verify the design requirements. So this is a really simplified example. The second thing we need to do is to define the conditions under which this block is supposed to operate. So one example is the fact that this block has a configurable shifting direction. So it can shift MSB to LSB or vice versa. And so one of the requirements for its operation is that once you start converting, you should not change the direction. And that's what we, again, without going into the details how this works, let's say that this here assumption takes care of that. And the second requirement is that once you start your conversion, you should not start again before the first one finishes. So this is implemented here in this second assumption. So at this point, we would need to start thinking how to make our checker as reusable as possible. And to do that, we would need to group our properties according to the nature of their requirement. And in this example, we can clearly see that they can be grouped according to whether they are testing some internal or external requirements. So what do I mean when I say this? We have a stable shift direction requirement saying that the shifting direction should not change during operation. And so this is a requirement for a valid block operation, but this is not a requirement which this block is supposed to ensure. It is supposed to be enforced by someone above it, someone who uses this block. So with respect to this IP, this requirement is external. Same goes to this no repeated start. And as for the checkers regarding the serial data and the valid indicator, they are actually internal requirements because they check something which this block is supposed to ensure. Okay, so logical question now is, why are we doing this? I mean, why do we need to group them like this? So the answer is, if we want to make this block reusable, these two external requirements, for example, on IP level, will have to be made assumptions because there is no external logic which will ensure that this is correct. So we have to instruct the formal tool to assume that it is correct. But when we reuse this checker on some higher level, we expect that this logic will be there. So we don't want to assume anything. We actually want to check it. And so we don't want to use assumptions. We want to use assertions. In other words, when we reuse this same checker, these assumptions will have to be converted to assertions. And if we have some kind of a naming convention for those properties, such as providing this prefix external requirement, then we can use a simple regular expression or wildcard matching to convert all of them at once into assertions. This approach, although has some flaws. So, for example, adding prefixes to the names of your properties is kind of ugly. You may disagree, but that's, I guess, my opinion. The second one is that it's error prone. So if you rely on the name of the property to do some modifications to it, then what happens if you make a typo here? So I don't know if you've noticed, but this here is actually a requirement. There is a typo. So if you use the wildcard or regular expression matching or something, this particular assumption will escape that, and you will have some kind of an assumption in your environment which should not be there. It might mask some bugs. So it would be good to have some kind of a hierarchical namespace separate for each of these assumptions, so properties. For example, it would be good if we could say external requirement dot stable shift direction. So it kind of specifying a different scope entirely. And there actually is a good way to do that using the generate statement. So we could have put all of them into a separate module, but there are also various drawbacks for that. For example, it pollutes the global namespace, and it makes sequence reuse completely inapplicable. So any sequences you want to reuse in both external and internal requirements, you cannot do that. But by using a generate statement, we are actually creating a separate namespace for all our assertions while keeping all declared sequences or properties or logic, whatever, visible to them. So for example, this stable shift direction defined like this now becomes functional verification dot external requirements dot stable shift direction. So without any prefixing the names, we have achieved this goal of having a name which stands out from others. So if we want to do some modification on the external requirements, we can just use this string, use the wildcard, for example, functional verification dot external requirements dot everything. Okay, so one more thing you may have noticed here is that the external requirements are actually assertions here. So why did we do that? And so if we think about it, if we think about the reuse of this component, the external requirements will have to be assumptions on IP level, but will have to be converted to assertions everywhere else they are reused. So whether you are reusing them on subsystem level or top level or basically anywhere, you have to convert them to assertions. But if we specify them as assertions originally, then we just have to change them once to assumptions inside this block level verification environment, which is what we did here in this example. This example is done using a Cadence Jasper Gold tool. As you can see, they are assertions by default, and using this simple tickle command, we just converted all of them to assumptions. If, for example, you find that some requirements are missing, you can easily just add them in this external requirements block, and using the same flow, they will automatically be converted to assumptions. So lastly, we will go over some of the examples of vertical reuse of a checker created this way. So if we now go back to the example of our command module, what do we have to do to have some formal verification of this module and include the checker we previously created? Basically, all we have to do is include the same file list which compiles our checker and bind it to the actual instance of this serializer. That's all you have to do. Just include the file list you already have, and you'll have a very similar structure to the one on block level, meaning that the top level entity is the design itself, and you have your checker bound somewhere inside. That's all you have to do. And you can see the results and benefits of this very quickly and easily. For example, in this design, we injected a couple of bugs to see just how our model our checker will detect it. And this first example, shows a bug in which this conversion start strobe is not connected properly. It is actually tied to 0. And as we can see, our checker reported that all coverage is unreachable, so we cannot do any serialization. Failing covers is usually, let's say, an outcome of a badly connected model. So in here we see how we, just by adding this one file, we detected a badly connected block. The second one is a bug which illustrates a missing logic, which ensures that there is no repeated start. And in this case, you can see that this assertion, no repeated start, failed. And due to it, of course, the internal requirements also failed. So basically, without any effort, we managed to find a couple of bugs there. Of course, not always will you have a conclusive results using formal verification. Very often, you will struggle with the complexity of the design. And one thing to notice is, for example, we already proved on block level that if external requirements hold, then internal requirements hold as well. So we don't really need to check them. It's just an extra job for the tool. It just wastes time and resources trying to check something which is already proven. So with this kind of structuring, we can easily disable them as well and say, okay, disable all internal requirements. I don't want to check them. I only want to check the external requirements. And in this example, we got conclusive results, but we only tested the external requirements here, again, done using the Jasper Gold tool. Additionally, we can leave the cover preconditioned cover properties for the internal requirements, just to have some kind of additional insurance. And lastly, this example shows how you can even reuse the component you designed for formal verification in your simulation environment. By using this, you can also detect badly connected blocks, but you can also make use of the simulator's features to analyze the assertion coverage. So in this particular example, we just included using the same block level file list. So again, the only modification you have to do to include this checker into your verification environment is to just add the block level file list to your elaboration flow. And what we see here are some coverage results after simulation. And as we can see, there is one cover property failing, which is probably an indication that our tests are not exercising this block sufficiently, and that someone who is doing block level verification of the block obviously thought that this should be covered since they covered it in block level verification. Okay, so to conclude, we demonstrated here an example of some techniques you can use to make your IP checkers more flexible, in the sense that they can be easily reused on higher levels with some benefits. There is some extra work on block level, such as structuring them according to their structuring properties according to the nature of the requirements, and adding those extra commands to manipulate the property directives. But in the end, if the intent is to reuse that checker on higher levels, then I guess it pays off. So that would be it. I hope you found this interesting. Thank you for your attention. And for any questions, just feel free to contact us at our booth.